Without mathematics, there is nothing you can do. Everything around you is mathematics. Everything around you is numbers. And hence, where there is a number, there is a beauty. Very good afternoon. Namaste to one and all. I heartily welcome all of you to the KLE Society GI Bhagavadi Arts, Science and Commerce College Nipani, Department of Mathematics, IQAC Initiative, 2 days, international webinar on complex analysis and its applications. Ladies and gentlemen, complex analysis is the study of complex numbers together with their derivatives, manipulation, and other properties. It is an extremely powerful tool with an unexpected large number of practical applications to the solution of physical problems. Once again, I welcome all of you to this webinar and hope that you all will have a great time ahead. I'm sure that you will all feel enriched with knowledge after completion of this event. First of all, I request distinguished personality, our beloved Vice Principal, Dr. R.G. Kharabe sir, to welcome all of you.
Good afternoon to all. We are hosting the IQAC initiative 2 days international webinar on complex analysis and its applications, organized by Department of Mathematics of our college. Today on 22nd July and tomorrow 23rd July 2020. On this occasion, today's resource person is Professor Rod Halburd, Department of Mathematics, University College London, going to talk on the topic complex analysis and special functions and integrable systems. On behalf of KLE Society Belgavi, Jai Bagadi College Nipani, staff and students, I wholeheartedly welcome you, sir. Also, tomorrow, tomorrow's resource person is Professor S.S. Kusnurmat, Department of Mathematics, Karnataka University, Harvard. He is going to give a lecture on topic Riemann hypothesis. I will also heartily welcome you, sir. Our chief patron, Sri Praveen Bagewadi, member Board of Management, KLE Society, Belgavi. I will also welcome you, sir. I will also welcome all the participant delegates from different countries who are registered and eager to participate in the webinar. I will also welcome Principal Dr. M.M. Hurdi, sir, Dr. Srimati M.M. Sakrikop, Madam, HOD of Mathematics, Dr. Ashok M. Rathod, convener of webinar, Dr. B.S. Kamble, IQAC coordinator, and all the staff members and student participants. Once again, I welcome you all and wish you all the best. Thank you.
Thank you, sir, for your warm welcome. Next, I call an incredible woman, our beloved HOD, Dr. M.M. Shankrikop, to give brief introduction about society and college.
Good afternoon to one and all. Chief Patron of today's webinar, Sri Amarna Bhagavadi, Member Board of Management, KLE Society, Belgavi, Honorable Resource Persons, Dr. Halburd and Dr. S.S. Buslumer, sir. Respected Principal, Dr. M.M. Hurudi, Vice Principal, Dr. Adi Kharabi, IQAC Coordinator, Dr. B.S. Kamble, learned colleagues and participants. I welcome you all to today's international webinar on complex analysis and its applications. It is my great pleasure to introduce our prestigious society, Karnataka Lingayat Education Society, Belagavi, our institution, department, and topic of today's webinar. Our educational society was established by 7 dedicated luminary teachers called Saptarshis in the year 1916. Today, our society has more than 270 institutions in which 16,000 dedicated faculty are serving their best to cater the needs of about 1,25,000 students every year. Society has been playing a vital role in academic and socio-economic upliftment of North Karnataka region by imparting education from KG to PG. Our society has offered different courses such as basic social science, management, tourism, hotel management, engineering technology, nursing, pharmacy, dental, medical science, agriculture, educational training institutes, etc. Further to its cap, it has collaboration with prestigious international educational institutions of UK, USA, Malaysia, China, UAE, and Zimbabwe. The great visionary, our beloved chairman, Dr. Prabhakar Kore, and Chancellor of KLE University, Belagavi, and assisted by the dynamic board of management, deserves special acknowledgement and spectacular growth that society has achieved the last 3 decades. Among the 15 aided higher education institutes, 10 have been at A level by NAC. This speaks of high standard of education imparted by our society in education institutes. Next, I want to introduce our college, KLE Society G.I. Arts, Science and Commerce College, Nipani. The college was established in the year 1961 with arts and science in a vision to provide quality education for the empowerment of the rural and linguistic minority youth of Karnataka and Maharashtra states. Our college is named after the principal donor, late Sri Ganapati Ishwarappa Bhagavadi, in the year 1966. Next, in the year 1977, Commerce Wing is started and college is renamed as KLE Society G.I. Bhagavadi Arts, Science and Commerce College, Nippon. Looking into the difficulty of rural and semi-urban students to pursue their postgraduate PG studies in 2010, M.Com in 2011, MSc Mathematics, and in 2018, MA English courses are introduced. Totally, we have the faculty members as 68, which are highly qualified teachers with 18 PhDs, 6 MPhils, and 6 are pursuing PhDs. And totally, we have the 1155 student strength, among them 675 girls. Our college excelled even in academic as well as sports. For the year 2018-19, UG results are 85%, PG results 100%, and totally we have 92 centum scorers, that is 100 out of 100 students in different subjects. We got 3 university ranks for the 18-19. Miss Sangeeta More, first rank in BSc, Miss Sabina Mullah, 9th rank in BSc, and Miss Nikita Jadhav, 3rd rank in MSc. And totally we have the University Blues 11. This speaks about our institute. Next, I want to introduce about Department of Mathematics. Department of Mathematics is established in the year 1961 with the subjects physics, chemistry, and maths. PG Mathematics is introduced in the year 2011. Unique feature of our department is it has a well-equipped mathematics museum. Department has 7 well-qualified faculty members with 2 PhDs and 2 registered for PhD. Research activities of the department are very good. 29 papers published in international journals, 5 papers in national journals, 5 papers in international and national proceedings, with a total 93 citations and 4H index. Results of PG and UG are excellent every year. We got 3 university ranks for BSc, so that is in BSc and MSc, Miss Nikita Jadhav got third rank in MSc. And also we have the 39 students, 100 out of 100 in mathematics subjects for the year 2018-19. It shows the quality of our institute. About webinar, I want to speak. Topic for the webinar, complex analysis and its applications. One cannot really visualize root 2, but one can visualize root of -1 and apply it in physics and engineering. This work is an exploration of complex analysis as a tool for physics and engineering. Although nothing in reality is a complex number. Our resource persons are going to talk on recent developments in complex analysis, such as applications of complex analysis in solving differential equations, special functions, and integrable systems. And tomorrow, sir is going to speak on Riemann hypothesis, which is a conjecture that the Riemann zeta function has its zeros only at the negative even integers and complex numbers with real part half. Many consider it to be most important unsolved problem in pure mathematics. It is of great interest in number theory because it implies about the prime numbers. And it was proposed by Bernard Riemann in the year 1859, after whom this hypothesis is named. Yes, I hope you can enjoy the sessions of today and tomorrow. Thank you one and all.
Thank you, ma'am, for your brief introduction about society and college. Friends, today we have with us an eminent personality, resource person, Professor Halburd, Department of Mathematics, University College London, who made a powerful contribution to the field of research. I request convener of this webinar, Dr. Ashok Rathod, to introduce today's resource person. Mute.
Colorado and so it is great pleasure to introduce our speaker, Dr. Rod Halburd. Rod Halburd is a professor of mathematics at University College London. He was born and grew up in Australia. He received his BSc from the Australian National University and his PhD from University of New South Wales. He worked at the University of Colorado and Loughborough University before starting the work at University College London in 2007. Halburt's main research area are integrable systems, differential and difference equations, Nevanlinna theory, and complex analysis. He has explored several properties that appear to be good dictators of integrability in both the differential and discrete cases. Many of these cases are complex analytic in nature. Sir has guided 9 PhD students and one MPhil student. Sir has delivered talks on several international conferences. Sir and Risto Karhan worked on classification of difference equations, proved some interesting results in pure Nevanlinna theory for the difference operator. In a series of papers, they proved difference analog of Nevanlinna's second fundamental theorem for finite order meromorphic functions and Picard's great theorem. Sir has several awards and honors. Sir has awarded with Australian Postgraduate Research Award by Australian Research Council, University of Colorado Excellence in Teaching Citation by CU Housing Association. And Sir is a member of IPSRC peer review panel. Sir has a member of London Mathematical Society and American Mathematical Society. He is a model for young researchers, and his work impresses lots of researchers to reach great heights. Thank you. Thank you, one and all.
Thank you, sir. Ladies and gentlemen, now we have the next part, talk by Honorable Resource Person. I request Professor Halburd, sir, for his valuable words.
Okay, so thank you very much for your very kind invitation. Just bear with me a moment while I start sharing my screen. The inevitable awkward moment in any talk these days. Okay, so if that's clear and if I'm clear and if you can hear me, can somebody just stick their thumbs up and let me know?
Yes, it's clear, sir.
Okay, fantastic. Thank you. Okay, so thank you very much for the kind invitation, and thank you very much for the kind introduction. So I understand that today there will be many master's students present, maybe considering PhD options and so on. So part of what I have in mind in putting this talk together is to put forward the case of why complex analysis. Why do we study complex analysis, and what can we do with it? So it's no doubt, I think, a beautiful area. I think any undergraduate who has seen it will acknowledge that. Certainly anybody who works in the field will acknowledge that. But it's also a very, very practical area. So in fact, although I've never actually taught an introductory undergraduate course in complex analysis, I would very much like to. I've always thought how I would introduce the course. And that would be to say that for the vast majority of people present, you will definitely find something to love in this course. It doesn't matter if you are the purest of pure mathematicians or the most applied of applied mathematicians and you just want to solve the problem. And if you have to solve the Riemann hypothesis or solve a quadratic equation, it's all the same to you. Wherever you are on that spectrum, complex analysis is a subject that you can find something really amazing and something to love. I would also say that unfortunately, if at the end of the course people haven't found something that they found interesting, then perhaps they'd chosen the wrong degree. Perhaps they kind of let the prospectus fall open in the middle page, which was somewhere around M. They said, I like maths, and they decided to do a good degree in it. So to me, complex analysis is the litmus test. There's something here for everybody. So I would in particular today like to talk about some aspects of what you can do with complex analysis that somehow go beyond complex analysis. You have some experts in your department. Dr. Ashad Rathod does some nice work in Nevanlinna theory. I will mention Nevanlinna theory a little bit as I go along, but I'm not going to make it a central aspect, but I will use it as a tool. Could I also just ask yourself on mute? Or I can do it myself. If you do have any questions, or if I'm unclear, or if my image starts to freeze and I'm not aware of it, please do feel welcome to interrupt. So today I would like to talk about using complex analysis to basically solve stuff, to find solutions in some sense of differential equations and perhaps some discrete equations. When I say in some sense, well, obviously, if I can write down the solution in terms of exponentials or trig functions or maybe elliptic functions, I think everybody would be happy. Will mean something slightly more general than that, because I can always say, oh, any function that I like is something that's a function that I can define however. If I can express other things in terms of it, to some extent, that's a solution. That might be true, but that's not what we usually mean. We usually mean that we can express a solution in terms of something with properties that we can ascertain beyond mere existence results. And that brings us to the notion of special functions. So special functions in general refers to things like hypergeometric functions, elliptic functions, things that are often given in terms of solutions of some kinds of equations. And I'd like to argue that in almost all cases, those equations are special because they're special when you look at them in the complex plane, even if you're not actually interested in the complex plane. You're trying to solve a problem in water waves or whatever. Integrable systems, to some extent, is the nonlinear version of that theory. So we can have much more complicated equations, and the methods used are much more complicated, but still we can either find some exact solutions or we can characterize the solutions in a much nicer way than normal. And I would like to use this as the application of complex analysis. So, as I said, part of this is to address maybe why somebody who's not naturally interested in complex analysis might like to do complex analysis. And I'd like to quote somebody who's going to appear later on. Oh, I've misspelled Panleve. That's really bad, but anyway. So if you correct the spelling, this quote is by Paul Panleve. It says, "The shortest path between two truths in the real domain passes through the complex domain." In other words, often the quickest way, sometimes the only way that we know, of solving certain real problems, in other words, problems that don't seem to involve the complex numbers, is to introduce these strange objects and simply use them as a tool. So often, for example, if we do surface teaching for the engineers, they insist that most of the course is complex analysis. Okay, that's not mathematicians pushing it on other disciplines. That's other disciplines, insisting that this be taught. So the main outline of this talk, the main theme, is to look at the singularity structure of mostly differential, but also a bit of discrete equations in a complex plane, and see that simple singularity structure corresponds to these equations that we can either solve exactly or that we can characterize their solutions in all sorts of other ways very nicely. Typically, people have looked at equations where all of the solutions are nice, where they have a particularly simple singularity structure. You might think meromorphic, for example. I would like to push that idea a little bit further to the case where maybe only some of the solutions have a nice singularity structure, other solutions are bad. Can we actually characterize the solutions that are nice? Okay, the solutions that seem to have these nice properties. And in all the examples I've looked at, wherever we've tried hard enough, that has indeed been the case. And this will be the application I was mentioning of this area of complex analysis called Nevanlinna theory, which is the value distribution of meromorphic functions. We'll also discuss a few other issues. So we will allow a little bit of branching and show that you can still have decent equations and solutions that you can characterize in a similar way. And I will mention another type of fundamental complex analysis problem, a Riemann-Hilbert problem. So this is a problem where you want to find a function that's analytic everywhere in the complex plane, except along a number of curves where you have a prescribed jump. So that might sound a little bit abstract, but actually it's exactly this problem that's solving certain equations that turn up in water waves and all sorts of areas turn up, as well as obviously in geometry and more pure applications. And finally, I will talk about some discrete analogues of these equations, where we're not even in the, so discrete equations, so initially where the independent variable is an integer. And I'll look at ways relying on some basic complex analysis, very basic, so I'll end up with something extremely simple, where we can get precise calculations of entropy that people had done in the past, either in a non-rigorous way or in a way that requires an awful lot of work. Okay, so let's start out with something very simple. Okay, so here I've written a simple initial value problem, so a differential equation with some initial condition. And well, it's very easy to solve exactly, but if you didn't know how to solve it exactly, you could always look for a power series expansion that's guaranteed by Cauchy's existence theorem, and you would come up with the answer that I've written here. By the way, when I scroll this arrow around on the screen, is that showing up for anybody there? Okay, well, I'm not sure, but I'll do it anyway. So in the middle we have a series expansion. It only converges for the modulus of z minus 1 less than 1, and of course it sums to the square root of z, which you could have got just by solving the equation by elementary means anyway. The point I'd like to point out here is that this is a branch point. Okay, so this solution, this function, the square root of z, has a singularity at z equals 0, which is known as a branch point. Now, I know that there are often master's students who don't quite get exactly what a branch point is. So since we're going to be talking about it a lot, I thought I would say a little bit about it. So here we have a function that's analytic, the square root of z. There's no problem with its definition. It's just the sum of this series, for one thing, in this region. So I have a circle centered at 1 of radius 1. The problem for us is at z equals 0. Now, I could always take some other point in this disk where this series still converges, so I still have a well-known function. Again, it's just the normal square root of z. And I can re-expand the power series there, and I'll get a series that will converge in a slightly different disk outside this point. So that's so what we can do then is uniquely extend the definition of the series. What happens, of course, when we try to do a closed loop around z equals 0 is that we get into trouble. So you can show that by doing this process, if you're marching around the circle e to the I theta, by the way, I was going to play around with different pieces of paper and cut them up and so on, but then I realized a few minutes ago that Zoom actually inverts all of the images, so I'm not sure if that's terribly helpful. But you would end up with this definition. Again, when theta is equal to 0, so in other words, you're at the point z equals 1, we would have the square root of z is 1, which is what I would have from here. But now, as I analytically continue to minus 1, in other words, when theta is equal to pi, then I would have that the square root of minus 1 is equal to I. However, I could also approach from the other side. I could also approach from the lower half plane, the point z equals 1, and I would end up with the idea now that the square root of minus 1 is actually minus I. So then I see that I get two different answers, so I can't actually define this function in even a continuous way on the plane. And there are two different solutions that people usually do with that. Maybe since you don't need to see the picture, I can just show you on this little small screen that you will have. So the standard one by, let me just see, because this is all inverted now. So the standard solution here, as I analytically continue around these two different answers, the applied mathematician answer is often just to split the complex plane like this and say, look, this point is nowhere near this point, so it doesn't matter that I'm approaching I in this direction and minus I in this direction, because, hey, look, they're well-separated points. But of course, we can do something that's much more sophisticated than that. The square root of z, of course, if I'm thinking of that as something whose square gives me z, then I always have two different answers. So I can put the one that we've defined here, where the square root of 1 is 1, on this piece of paper. I could do the same thing with the square root of 1 is minus 1, and then that would extend with the formula here, square root of e to the I theta is minus e to the I theta on 2. And now the problem is square root of minus 1 is, square root of 1 is minus 1, and over here the square root of minus 1 from above, coming from above, would give me minus I. And then you do the usual thing, make those two copies that you'd taken, you glue the top sheet of one to the lower sheet of the other, and now I get a function that I can analytically continue around. The I agrees with the I on the other side, so I keep going around on the second sheet, and then I come back. And if I step into the fourth dimension so I can glue those two remaining edges, I now have a double sheeted object on which the square root of z wants to live. So it's not what the square root of z wants to live on something smaller than the complex plane, it wants to live on something bigger. Now, that means that branch points in general make things much more complicated because the surfaces they want to live on are at least as complicated as this. Often if it's a logarithm, it's an infinite helix of these things. And then you can have branch points at different sheets of those branches. And that's what happens with generic solutions of differential equations. They're incredibly complicated in the complex plane. So let's have a little look at linear ordinary differential equations. So here I've written down a very important one. This is the hypergeometric equation. And if you think, if I give you u and u prime, and I want to find u double prime, then of course there's a problem when z is equal to 0 or when z is equal to 1. So when I solve for y double prime. Now, it turns out for linear equations that these points, the points where once I've solved for the highest derivative, things become singular, these are the only points where the solution can become singular. And that's something very nice about linear equations. It's not true about nonlinear equations. So if I have a look, so as I said, in general, the solution is branched around z equals 0, but there is one solution. So this is the famous hypergeometric series of Gauss that does converge on a disk of radius 1, excuse me, centered at the origin. Now, the remarkable thing about the hypergeometric equation, which is because its singularities is so nice, that I can look at the expansions around all the singular points here and express them in terms of the one series. Okay, so this one function f, I can express everything in terms of, so the ABC here just refer to the parameters. So this is the fact I've already written down. One of the solutions at 0 is just given by f. There's another solution with some weird power of z times the f. The main thing here is that f is analytic at z equals 0. It doesn't matter that the coefficients of the parameters have changed. So in general, these things are only valid when certain combinations here are not integers. So in particular, 1 minus c is not an integer. So this will have branching. So although one of the solutions is branched, the other solution, sorry, is not branched, the other solution is branched. And as I analytically continue from one solution to another, then even the one that wasn't branched will pick up branching somewhere else. But you can express all of the solutions in terms of this this one quantity. So these are the expansions around the singular points 0, 1, and infinity. And this is one of the things that makes the hypergeometric equation so special. So many of the special functions that you know, things like Bessel functions, Airy functions, are actually limits of the hypergeometric equation. You introduce some transformation depending on a parameter, so that these 3 points, 0, 1, and infinity, can now be moved around depending on the parameter. And you take a limit when two of them merge together, and then you get the confluent hypergeometric equation. You do it again, you get Bessel, and so on. The fact that we have these nice representations of the solutions together with some integral information means that we're able to calculate something called monodromy. So that means that I can start out with some solution at some point, and I can analytically continue it along any curve in the complex plane and then come back again. Now, in general, because we have all of these branching behavior, I'm not going to come back to the same solution. But what I come back to is still a solution of the differential equation. So it will be a linear combination of whatever basis I choose. So if I take two basis vectors, analytically continue them around and come back again, I can express that new vector in terms of the old one by a constant matrix, and that's a monodromy matrix. And that is something that I will mention a little bit later, but we don't need it for now. Let's have a quick look at nonlinear equations. So here is an example of a simple nonlinear equation. Now, this equation clearly has a problem when the independent variable is z equals -1. And that's reflected in the solution, which I've written down here. So indeed, when z equals -1, I have a square root branch point again. So I have a problem, as I might have expected. The difference with nonlinear equations is that they can have singularities at other points as well that are not where, you know, at points where the equation itself is not obviously singular. In other words, there's nothing weird about the z dependence. So here, for example, there is a singularity when z is -1 over c squared, but c is just this initial condition. So as I move from one solution to another by choosing the initial condition, that solution, that singular point on the solution can be placed anywhere that I like. So this gives us a difference between a fixed singularity, the only type that you have for linear equations, singularities that occur where the equation has a problem, and movable singularities that depend on initial conditions. And this is an important distinction for us, because one of the key properties that have turned out to be extremely useful in the business is the Painlevé property. So an ordinary differential equation is said to possess the Painlevé property if all solutions are single valued about all movable singularities. So single value just means that there's no branching, it's not a branch point. In almost all applications, that means that it's a pole. But you could, in principle, have, and there are a few examples where you have movable essential singularities. Most of the time, it's just a pole. So let's have a look at a simple first order equation. dy by dz is a rational function in z and well, it's a rational function in y. The coefficients can be anything that's analytic in some little neighborhood. The only equation of this type that has the Painlevé property is the Riccati equation. So the right-hand side has to be quadratic in y, but there's no restraint at all on the coefficients apart from the fact they have to be analytic somewhere, because that's what we started with. But there's something very special about this equation beyond its form. It's the fact that it is basically a linear equation in disguise. And linear equations are things that we know a lot about. We know a lot about their solution structure. We know a lot about, well, the solution space. It's a vector space. You just need a basis and so on. So basically, to solve the Riccati equation, we have to write down an auxiliary second order linear equation, and then the solution of the Riccati equation is given by a logarithmic derivative. So you can even see here the origin of the Painlevé property, because I've already mentioned the fact that a linear equation can only have singularities where the equation itself is singular. So that means that there's something singular going on with these PQR. So either P vanishes or PQR are singular somewhere. So W can only really have a singularity at fixed points. Okay, so there are only fixed singularities of the original equation. However, Y can develop other types of singularities coming from the fact that this is a logarithmic derivative, but they are just points where W vanishes. So the only points where W is analytic and I have a problem with the logarithmic derivative is where W vanishes, but of course then it's a logarithmic derivative of a zero as a pole. And so then we can see that the only other singularities which can vary with initial conditions are poles. So right here we see that the only movable singularities are poles. But this is the first example where we see singularity structure pinning down what is an integrable equation, an equation that is in some sense solvable. It's just a linear equation in disguise. It gets more interesting when we move to higher dimensions. So the first example of using singularity structure, so a special case of the Painlevé property, actually goes back to the 19th century in the work of Kovalevskaya. So she noticed that the equations of motion of a spinning top, which depend on 6 different parameters, well, there were 2 cases previously known by from Euler and Lagrange, where the solution of the equation had been found. And Kovalevskaya noticed that those solutions, if you thought of them as complex functions, even though of course here we're talking about a top, everything's a function of time t, which you think of as a real variable, but if you just imagine everything as complex, then the solutions that were found were in fact meromorphic. So she asked herself, well, for what other choices of parameters is the general solution meromorphic? And she found one other case, and she was then able to solve that using the then new theory of theta functions and hyperelliptic functions. And that is the last case that's ever been solved of these particular equations in the 120, 130, whatever it is these days, years since then. That's the first case of using it very, very effectively to find solutions. And you might ask, well, is it really practical? Who cares about exact solutions? Well, exact solutions are the kind of concrete examples of things. So even if you're working in a very pure area, or if you have some geometrical object, some object in differential geometry, it's often described ultimately in terms of differential equations. And so if you actually want a concrete example of something rather than just an existence result, you are asking for integrable cases of whatever it is that you have. And those things are often important in their own right, usually, but often just for building intuition as well. Anyway, so Kovalevskaya, because basically her equations were constant coefficients, so there were no fixed singularities. So the Pan-Lavie property more or less degenerates to saying that all solutions are meromorphic. The more or less being this fact that, you know, we're demanding poles in that case, which is slightly stronger than essential singularities. So Pan-Lavie, Gambier, and Fuchs, excuse me, soon after, so around the turn of the 20th century, did a classification of all equations of the form y double prime is a rational function of y and y prime, where the coefficients depend on z, excuse me, with the Pan-Lavie property. And they were able to show that all such equations fell into 50 different classes. And effectively, they were able to solve all of them, provided that there were 6 equations that you could solve. So many of these equations you could solve in terms of known things like elliptic functions. But to get the rest, you needed just 6 new differential equations. And in terms of those things, then you could solve whatever was left. Excuse me. And those equations today are known as the Pan-Lavie equations. So here I've written down the first two simplest looking equations. The main thing to note is that these equations are non-autonomous. So Z is the independent variable here, so it appears explicitly. And all but the first equation involves some parameters. So here I have a parameter alpha. These equations were studied a bit in the 20th century, but by and large they were ignored until around 1980, when these equations kept turning up as reductions of certain important equations, solitone equations that appeared in the theory of water waves, fluid mechanics, general relativity, everything. There are a bunch of nonlinear equations, nonlinear partial differential equations that people realized you could say something very nice about the solutions. The other thing that was discovered, in fact for P6 it was already known about a century earlier, is that these equations are in fact the compatibility conditions of some linear problems. So they're not linear themselves, and you can't change them to linear equations as we did for the Riccati equation. But there is a linear spectral problem lying behind them, which is related to the monodromy issue that I described earlier, which if I have time, I might say some more about. That means that although these equations define new functions, so new functions that we haven't seen before, we can say a lot about the nature of these functions. So in that respect, they deserve to be new special functions in the same way that trigonometric functions and elliptic functions are. And indeed, in the modern version of Abramowitz-Stiegen, which is the digital library of mathematical functions, there's a chapter, I think it's chapter 34, specifically on the Pan-Lavie transcendents, which are the solutions of these things. Now, there's a related theorem that goes back to Malmquist, but was in a special case of it, which is the one I'm describing here, was reproved using Nevanlinna theory by Yoshida. And that is the following. Suppose that I have the same kind of, well, it's not exactly the same. So suppose I have w by dz is a rational function in w and z. Okay, so here I have to be rational in z as well. Then this equation admits a transcendental meromorphic solution. That means a non-rational meromorphic solution, if and only if the equation is the Riccati equation, or of course, if A is 0, then it's just a linear equation. That also holds the same as before. So this is neither stronger or weaker than the result of Panleve. It's both stronger and weaker, however you want to think about it. It's stronger in the sense that here I'm talking about just one solution. Okay, so I'm making an assumption about one solution, whereas for the Panleve property, I was making a solution about all solutions. All the solutions had to be nice. It's weaker in the sense that here I have to demand something about the nature of the solution. It has to, firstly, it has to be non-rational. It has to be transcendental. And also, it has to be globally meromorphic. I can't allow fixed singularities. So I'm going to miss some things in that respect. But it results in this direction and the difference between these two things that I would like to explore a little bit, because the ideas behind the Malmquist theorem means that we can start to look at individual solutions and talk about their singularity structure rather than the whole solution space. The way that the classification work of Panleve and so on developed is really to look for bad behavior, look for branching, and as soon as you find it on one solution of your equation, you throw it out. But here you have to be much more subtle. There might be other solutions that have bad behavior. So just because I find branching somewhere by some series expansion, it doesn't mean that branching is on all solutions. It doesn't mean it's on the solution that I'm interested in. So it's a much more subtle thing. Here we have to talk about one solution at a time and demand that we know enough. And that's the idea of this question that I've had below. Basically, can we find integrable subsystems? Can we find special solutions of otherwise non-integrable, non-solvable equations where I can say something about the solution? Somebody's written on my screen. So I'm going to briefly mention two results of Nevanlinna theory. So you have an expert on Nevanlinna theory in your department. I'm sure that this is an area that it's a very beautiful area. I'm not actually going to go into any of the details. Nevanlinna theory is the theory of meromorphic functions, the value distribution of meromorphic functions. But usually by the time you set up all the machinery, then either people have seen it before or the people who haven't seen it before are kind of, glazing over and drooling on their desks, which I can't see because your videos are off. But I only really need some simple results that come from that. And these are basically results that say that if I have a solution of a certain kind of differential equation, I know that it takes certain values a lot. So I'm giving it to you in a relatively simple context. Nevanlinna theory can make this a much more general result, but this is the one that's easier to explain. So as with the Malmquist result, suppose that we have a transcendental, that means non-rational, meromorphic solution of a differential equation where basically I can isolate a high power of y. This is just a special case of Clooney's lemma. So I have a high power of y is equal to some terms involving derivatives of y and powers of y. As long as the degrees of those terms are all no bigger than n, then I can apply this theorem. So what do I mean by that? So if I have a term like y squared times y double prime, since there are basically 3 y's in there, that's a term of degree 3. Sorry, could someone stop? Thank you. Yeah, so we can't have 2 high terms on the right-hand side, that's all. This is a very general result. And the conclusion is that my non-rational meromorphic solution then is going to have an infinite number of poles. And that's the kind of result that we really need from Nevanlinna theory to do the kind of analysis that I'm describing. There's another result in a similar vein, and that is that if I have a differential equation, like this one down here, So again, this is just a differential polynomial in y. There's no constraint on its degree or anything. If I replace y by some constant a, and this equation is not solved, so we get something non-zero on the left-hand side, then the conclusion is that y takes the value a an infinite number of times. So the first one concludes about poles, the second one concludes about finite points, and these are the kinds of results that are incredibly useful for us. So now let me have a look at an equation kind of motivated by the second Penalvé equation, but that doesn't matter for now. So I'm just looking at this fairly general looking second order differential equation where f of z and g of z are as yet unspecified functions that are analytic in some neighborhood of z naught. They might be rational functions by the time we want to apply Nevanlinna theory or something, but at the moment they're just analytic at some point. Now, since f and g are analytic at the point z naught, they're finite. So, so if I want to analyze what happens near a pole of y, if there is one at z naught, then I can see immediately that if y has a pole of order p, then the left-hand side has a pole of order p plus 2, and the right-hand side has a pole of order 3p, because the second two terms are lower order. So it must be a simple pole, and then it's very simple to see the coefficient, in that case, the residue is plus or minus 1. So that means that I have a series expansion of the form given here in red. So then I could substitute that expression into my equation, equate coefficients term by term, and I'll end up with what's called a recurrence relation. Okay, so a way of calculating an in terms of some polynomial of all the previous an's, or the lower order an's. And what you can see there is, so we know what a naught is, it's plus 1 or minus 1, and then I can calculate a1 and a2 and a3, but there's a problem when n is equal to 4. Because the right-hand side has already been determined now. I already know what a naught up to a3 are. Can whoever's writing on the screen please stop? And the left-hand side is 0. So that will give us a non-trivial constraint on our coefficients. And in this particular case, if you work it all out, then it's given by this differential relation at the bottom. Okay, so that's what I'm about to follow through on the next page. So this, here I'm just repeating what we had. So now I can do one of two things. Firstly, I could say, well, suppose that f and g are rational functions, then Clooney's lemma, one of the things I said from Nevanlinna theory, guarantees that I have infinitely many, y has infinitely many poles, so they can't all be at the singularity. At infinitely many points. So f and g are rational functions. This is a rational function. If something is satisfied at infinitely many points, it must be satisfied everywhere. Now, if I had that true for both types of pole, epsilon equals plus 1, epsilon equals minus 1, of course, I just get that f is linear in z and g is a constant, and I'm left with this equation down here. And this is, well, if a is 0, you can solve this in terms of elliptic functions. If a is not 0, then it is transformable to the second Penalvé equation. Now, in the case of Penalvé analysis, you don't assume that f and g are rational. This would tell me that I can't, unless this is satisfied at some point, I can't find a Laurent series expansion. What you could then do is you could go back and you could show that I can modify the Laurent series. I have to add in some logarithm terms, and then I get something that satisfies the equation. But that's obviously branched. So in other words, the argument there is that I'm always going to be able to find a branched solution branch around z naught, unless this condition is satisfied. That holds for all z naught and all epsilon, okay, plus 1, minus 1. So that's what leads me directly to the Penalvé equation. But in the case of Nevanlinna theory, I only know that there are infinitely many poles. I don't know that there are infinitely many poles of both types. So if I have them of both types, again, I have the second Penalvé equation. But if it's only one type, you can actually show then that you do still find some solutions. Y then is given by a solution of a particular Riccati equation, which we've already seen before, and nice, we can solve them in terms of linear equations. So here, even when this equation here is relatively mean and it has lots of branch solutions, there would be some, and they're characterized by this Riccati equation. And that's the kind of result that would be useful, because then we can, even for non-integrable equations, we can find some solutions. So taking that idea, there are more complicated equations that one can look at. So for example, the equation at the top here was first written down by, or the normalized form of an equation written down by Walter Heyman as part of a conjecture about coming from Nevanlinna theory, and I needn't go into that. But the idea is that we should really be able to find all of the solutions to this equation anyway. Hello, can you hear me?
Yes, sir, we can
Hello?
hear.
So did I just dropped out then? Did it? Was I out for long?
Yes, sir, you can continue.
Yeah, was I out for long, or did I just drop out for a few seconds?
So sorry.
Okay, so I will. Well, I'll. Where?
Sir, you can continue with the session. No problem at all.
Okay, thank you. Okay, so I'm not quite sure at what point I dropped out, but I was just describing the fact that the location of the resonance, okay, so the point where we might get some interesting condition, which is the R here, depends on the alpha, beta, and gamma, and they can vary from point to point. So in that respect, it can be quite messy, but nonetheless you can do this. When R is not a positive integer, you don't have any resonance at all. You don't have any, you're not going to hit this value. So you can generate a formal series and it will be unique. So there are ways of dealing with that situation. So Hille, Omenko, Kont, and Ng have been using them, but R can still be an integer and it might be 127. So we don't want to have to go out all the way to check these things, but there are ways of getting around that. So I first did this with constant coefficients with Yikman Chang and Hong Kong University of Science and Technology. We did the rational, or we did the non-constant coefficient case with Jun Wang at Fudan University in China. And my PhD student who recently finished has looked at this more general class. So the upshot is that you really can find these solutions, but here we really need Nevanlinna theory, or something like Nevanlinna theory, because we need to know that we have enough singular values. The singular values here occur when W is equal to 0, because that would be the problem when I'm trying to expand to get the value of W double prime. So I need to know that I have a lot of zeros, and then I can get some series expansions that in general are going to produce some problems, and I want the problems, I want the obstructions, because that's what reduces it down to special equations. You can allow for a small amount of branching. So in general, the branching in differential equations is absolutely horrendous. So again, I could have a branch point and you have a bit of a look around and you'll see some other branch points off in the distance. But now imagine that I loop around a branch point and I come back on a different branch and I have a look around, and now all of those branch points will have moved in general. And in fact, they can even start clustering together. So you can get an absolutely horrendous global branching behavior. And that's why Painlevé started looking at the Painlevé properties to specifically have functions that could be written as single valued on the one surface. Okay, so you just puncture the surface at the fixed singularities and you look at the covering surface. The next best thing are algebraic functions. And so algebraic functions are algebraic over the meromorphic functions. Okay, so they solve a polynomial where the coefficients in the polynomial are meromorphic functions. So they have n, in this case, branches. So Malmquist actually also looked at first order equations allowing algebraic solutions. So non-algebraic algebraic solutions, that's the analog of non-rational meromorphic solutions. So although Yosido reproved the case where Y is meromorphic using Nevanlinna theory, these ideas where we allow a finite amount of branching are important, and they can also pull out special cases. Oh yes, hello, please, go ahead. Yes, go ahead. Sorry, I can't hear anything. Do you have a question? Your hand is up.
Sorry, sir, for the little bit disturbance. Sir, you can continue.
Okay.
Sir,
okay, so so the idea here is that really we should be able to allow for a small amount of branching. It also makes sense if you take something with a Panleve property and you do a simple change of variable, you change the dependent variable to something like w cubed, then in general you're going to introduce cube root branch points, but you haven't changed the solvability of the equation really. You've made the solution algebraic. And if you're looking at applications, then quite often the equation that you're given might not be in the optimal coordinates, and so then you simply have to deal with that. So so another direction that can be followed is to look for equations that have algebraic solutions and use a known algebraic version of Nevanlinna theory. And again, Dr. Ashok Rotha is an expert in that area. Obviously, from the Panleve perspective, we would like to allow these A's, these meromorphic functions, to actually be branched at fixed singularities. That's the more natural question. But at the moment, if you do that, then you lose the power of Nevanlinna theory, which is something that I think should be extended, and that's why that's something I might refer to at the end. So another former PhD students of mine, Tom Kecker and I, considered some simple second order differential equations with non-algebraic algebraic solutions, or in the language of Nevanlinna theory, admissible solutions, but that I don't have time to explain what that is. You can rapidly see that such an equation has a form like I've given in blue here in the center. We consider the case where we just have one term on the bottom. So we have y double prime is a particular Laurent polynomial in y, and again you can answer the question. Okay, so you can find all of these. You can characterize the algebraic solutions, and they're related to either elliptic functions, the fourth Panleve equation, or Riccati equation. This might just sound kind of tedious, that, you know, okay, you're just asking a question and then you're going to find all of the things solving this property. But the point is that for a differential equation, an arbitrary nonlinear differential equation, you haven't got a hope of saying anything about any of solutions. Okay, but you can do a local existence, maybe you can even do some kind of global existence, but you can't, even though that's actually quite rare, but you know, you can't really get your hands on things. So the fact that you can ask for solutions of a certain type, characterized by singularity structure, and characterize them in terms of known things, is extremely rare. There's only one other approach that I know that does this, and that's the Lie symmetry approach. So basically there are only two approaches in town that I know that you can apply to fairly general differential equations. You can look for symmetries, that's the more well-known approach, and there's this one, the one of looking at singularity structure. So I have, I think, about 8 minutes left. So I just wanted to quickly point out that there are also these integrable partial differential equations. In fact, they were recognized as being integrable before the Painlevé equations. The classic example is the Korteweg-de Vries equation written here in red, which turns up in the theory of water waves. So it was written down actually by Boussinesq before Korteweg and de Vries. Both of them were in the 19th century. But it was in the 1960s that people realized that there's something special about this equation. And then they started to see a whole bunch of different properties. It has infinitely many conserved quantities. And the thing that really drives it is that this nonlinear equation is the compatibility condition for this pair of linear equations that I've written here in blue. Compatibility means that you just need to check that the cross derivatives matter. There are two ways of calculating the third derivative here with two x's and a t. So if you set both of those things equal, gamma here is just a constant that you can set to be what you like for convenience. Lambda here, this parameter is a spectral, is a so-called spectral parameter. And as in general, lambda would depend on time, but if lambda doesn't depend on time, then this system is only compatible if U satisfies this equation. The equation on the left here is remarkable for two reasons. Firstly, it's effectively an ODE. The derivatives are just with respect to x. So everything depends on t, but the equation part of it just depends on x. The other remarkable thing about it is that this is the time-independent Schrödinger equation from quantum mechanics. And lambda here is basically the energy and U is the potential. And the basic way in which these equations are solved is I give you the initial condition at t equals 0. So then I have a particular function U of x. Now, in general, we can't solve this equation explicitly, but we can extract certain data from it called the scattering data, again, because it comes from quantum mechanics. This equation then tells you that that scattering data evolves in a very simple way. And then you need to put that back into this equation saying, okay, now I know the scattering data, find what the potential was. That's called inverse scattering. And that's how you solve this partial differential equation from water waves, basically using quantum mechanics. But the point I wanted to, one point I wanted to make out is that that solution process actually depends very much on complex analysis, and in particular a Riemann-Hilbert problem, which is, as I said earlier, the case where you have an analytic function, a function that's analytic everywhere except on a curve where you have some prescribed jump conditions along those curves. The other thing I wanted to point out is that if you do symmetry reductions of this, so you look for subspaces of solutions given by ordinary differential equations, and that relies on the existence of symmetries, and these things have lots of them, that's how you get Painlevé equations. And that's how Painlevé equations came back to the notice of everybody at the end of the 20th century. And that's how these other properties were kind of later discovered, that to some extent should have been discovered first, because they're ordinary differential equations, and these are partial differential equations. So let me quickly mention something about some discrete equations. Here is the third Painlevé equation. So far I've only written 2 down, there were 6, remember. It depends on 4 parameters, but if one of them is 0 and 2 of them are not, you can rescale it so it just depends on one parameter, on beta. And then there's a solution generating method for, so if I have a solution of this equation for some particular value of beta, then I can construct another function w that solves the same equation, but with beta shifted by 2. Okay, so again, I take a solution of this equation with the parameter value beta. I construct the right-hand side of the equation here, and that will solve the same equation, but with beta shifted up by 2. And there's a similar story for beta shifted down by 2. And if I now just add these 2 equations, you'll see that the derivative terms vanish. And in that case, I end up with the equation that I've written down here. And have a look at that equation a bit. So originally we had a differential equation in x. X is now just a parameter. So x isn't being messed with at all. There's no derivative with respect to x here. But what was a parameter in the original equation is now being messed with. W depends on beta at these points, but beta plus 2 and beta minus 2 over here. So this is actually a discrete equation. And this is an example of what's called a discrete Painlevé equation. And it has all sorts of remarkable properties. It is also the compatibility condition of a linear problem. And it also has a continuum limit to the first Painlevé equation. Okay, so not the third, which is where it came from. It's from the first. And this is part of a general structure that we now know for these equations, that there are a vast number of equations of various types of discrete equations and differential equations. And some of these equations are effectively symmetries of other equations, and beautiful theories being developed by Sakai and others. This was one area that interested me for quite a while. So if you look at these difference equations, what kind of properties are there that distinguish these equations from other discrete equations? In other words, these nice Painlevé equations that have these extra properties. Again, there are various approaches. One that I looked at used Nevanlinna theory, which I'm only mentioning again because I know that there's a lot of Nevanlinna theory going on in your department. But yeah, as I say, there are other approaches. So I was going to go and mention some simple ways of actually calculating things like entropy for these equations, but I don't think I have time. So I think I might just quickly tell you a little bit about these equations. Okay, so some of these discrete equations turned up. Actually, the first case was in the theory of orthogonal polynomials. The first case where it was recognized as some kind of a discrete Painlevé equation came in quantum gravity in the 1990s. As I said, we know of linear problems for these equations. They also come as reductions of lattice versions of things like the Korteweg de Vries equation that we'd already seen. For discrete equations, there are various measures of complexity that one can look at. You can think of the Nevanlinna characteristic also as some measure of complexity. But more generally, you can imagine iterating this equation. I give you y0 and y1. The nth iterate is going to be some rational function of y0 and y1. And you can ask basically how the degree of that rational function grows. And that's a natural measure of complexity, and that's quantifying that basically gives us this notion of algebraic entropy. These equations have singularities. There is a nominal notion of singularity confinement, a fairly naive way of analyzing these singularities, or there's a much fancier way using blowups and algebraic geometry. But everything that I know that relies on us pulling out these nice equations involves us doing some analysis of singularities, including the work that we did with Nevanlinna theory. There are also some kind of number theoretic approaches that can be done as well, but I think I've used up my time, so I think I will just leave it there. So thank you.
Thank you, sir. So now we have interaction with the participants. So just few more minutes, sir.
Sure.
So I request the participants, anybody is having questions, so you can raise your hand. Yes, participants, if you want to interact with sir, please raise your hand so that we unmute you. Yes, participants, requesting to interact with sir. So anybody is having questions, please raise your hand so that we make unmute.
Obviously, anybody's welcome to drop an email. You know, usually with my email address on the poster.
Okay. Thank you, sir.
Thank you.
Enriched with knowledge about complex analysis, complex variables, derivatives of complex variables. Sir, by your words, what we can say is characteristics of complex analysis that makes it especially beautiful. Inside of it, we find objects that appear to be very complicated but happen to be relatively simple. Once again, wholeheartedly, we thankful to you, sir. Felt blessed by your words. Now, last but not the least, vote of thanks by organizing secretary of the webinar, Miss Girija Karuguppi. Sound up this time.
Excuse me, Kate ma'am. You can mute everyone, please. It creates so much choice.
Girija madam, 1 minute. Girija madam, you continue.
Okay. Thankfulness is the beginning of gratitude. Gratitude is the completion of thankfulness. A very good evening to all. I, Ms. Girija Karguppi, organizing secretary of this webinar, feel privileged to propose vote of thanks on this occasion. First of all, I wholeheartedly express my gratitude to today's honorable resource person, Professor Halburd, Department of Mathematics, University College, London, for gracing the webinar with his presence and took out valuable time of his busy schedule. I must mention my deep sense of appreciation for his work. I would like to extend a special thanks to today's chief patron, Sri Amar Bagewadi, member, Board of Management, KLE Society, Belgavi. I also extend my hearty vote of thanks to our beloved principal, Dr. M.M. Hurudi, and beloved vice principal, Dr. R.G. Karabe, IQAC coordinator, Dr. V.S. Kamble, for providing encouragement and support. I am very much thankful to our beloved Dr. M.M. Shankrikov, head of the department, for her infinite support and advice, which have greatly helped towards the successful organization of this webinar. I take this opportunity to thank all other dignitaries, technical committee members, and members of organizing committee for their valuable support and suggestions to make this first session of webinar a grand success. Lastly, I thank all the participants for their active participation and hope all are enriched with the knowledge. Once again, I thank all for your cordial cooperation. Tomorrow we meet again at 11 a.m. second session of this international webinar with one more eminent resource person. Till then, stay home, stay safe. Thank you.
Thank you.
Thank you, sir.
Hello, sir.
Hello.
Hello. Thank you very much, sir. Your talk was very informative and very interesting, because many of us don't know how to solve the differential equation with the complex variables. We know only how to solve the differential equation with the variable coefficients with the real functions, and it was very informative and very much thankful for you, sir, for giving the nice talk. And tomorrow, if it is possible, sir, you please join again Busman at 11:10. But it was very early for you, I think, sir. Tomorrow it will be very 11:10 Indian time, sir.
Okay, yes, thank you. I will. Thank you.
Thank you very much, sir.
Sir, for so inspiring for young researchers like us. So we'll adopt all knowledge, we'll solve some equations, and we'll do something better, sir.
So yeah, I didn't go much into actually the exactly how you use these to solve equations, because that involves actually loads and loads of formulas. But I think particularly because of an interest in Nevanlinna theory, I think that this is one of the areas where you really can use Nevanlinna theory to do something that is beyond what Nevanlinna theory is naturally interested in somehow. Because I think it becomes a bit of a problem when an area just answers the questions that come from inside. And I think that here, you have application, including algebroid, Nevanlinna theory of algebroid functions. They really do arise naturally, because these maybe simpler methods that people have used, these relatively naive methods where you look at a differential equation and you say, oh, I wonder what happens if I expand in a series around some point, and you start to get information. But really to apply that to an individual solution, you need to know that your function actually hits that point. And that's what Nevanlinna theory is really good at. And so, so Nevanlinna theory, through things like Clooney lemma and so on, will tell you that yes, if there's a meromorphic function, it will have a lot of poles. And so now if you try to find a Laurent series expansion and you get a contradiction, then you've learned something. And usually get very, very strong constraints that way. But also in line with some of the things that you're doing, I think that Nevanlinna theory really needs to be extended a bit, because there are two kind of gaps. I think one is requiring that it's meromorphic throughout the whole plane. So that is, it's interesting, but it's too strong from this point of view. You want to allow fixed branching. And the other thing is the notion of admissibility, which of course, in the case I used it in a talk, that was the idea that if I had rational coefficients, I want non-rational meromorphic solutions. But then you can't say anything about the rational solutions with these methods. And for more general coefficients, it's an even bigger problem. So I think that they're the two issues that I would kind of push for extensions to Nevanlinna theory.
Thank you, sir.
You're welcome. Thank you.
Sir, good evening, sir.
Hello.
Sir, this is Mahesh Barki from Davangere University.
From Bangalore.
Sir, I have one question for you. Sir, I am working on upper half disk Nevanlinna theory. Sir.
Sorry, I missed that. You're working on what?
Upper half disk Nevanlinna theory for upper half disk, sir.
For a disk.
Yeah, sir. But I am not getting counting function for upper half disk. How can I get it, sir? So please help me in this regard, sir. I will personally conversation with you, sir.
Certainly, feel free to say me something. So there is Nevanlinna theory in the disk, but it's always it's weaker than Nevanlinna theory on the whole plane. Similarly, there's Nevanlinna theory in a half plane, but you have much more constrained growth.
Yeah, sir.
But I still think that there are interesting things there. And one thing I worked on with a previous student of mine, but we never quite quite got it as strong as I would like, is that there are ways of kind of modifying the region for the kinds of purposes, at least, that we need here. That
I have find out all the basic theorems, sir, for Nevanlinna theory for upper half disk. But I am struggled about finding the counting function for upper half disk.
For a finite disk, you said?
Yeah, sir.
Well, I mean, I don't know it off the top of my head, but I thought it's just the usual counting function with a slightly different weight that you integrate to get the capital N. I guess the point is that it all, everything starts effectively from Jensen's formula, which you can still write down in the disk. But the main problem usually tends to be that you have to have a non-trivial minimal growth of your functions to be able to get the kinds of value distribution results that you get in the whole plane.
Yes, sir. Okay, sir. Thank you very much, sir. I will contact you personally, sir.
Okay, please do. Thanks.
Thank you, sir.
Sir, I have a question, sir.
Yes.
So now my friend Mesh Barke asked that question means is Nevanlinna theory is valid for means half disk? He asked that means is exists that area.
Oh, sorry, half disk.
Half disk, sir.
Okay, that I don't know. I mean, at some level, it's Nevanlinna theory really wants to live in the plane. And obviously, you can take some region and you can do some mapping from the region to another region. So you can map the half disk to a full disk or to a half plane or something like this. But usually whenever you're doing these things, you come up with these same problems of growth. I guess I would. So the very short answer is I don't know. I guess my for a half disk. But my next question would be is to some extent why the half disk? Is there something special in the half disk? Do you expect something in particular?
Yes, sir.
Yes, sir. Some functions are exist in the upper half disk only, sir. That's why we are interesting on upper half disk Nevanlinna theories.
Mm-hmm.
Means Goldberg and Ostrowski in 1970 or something that range, sir. They have gave a transformation that upper half plane to upper half plane, sir.
Mm-hmm.
So using that transformation means our sir, Busnumat sir, Mesh Barke, and we did work on that and solve that equation, but means that counting function that doesn't exist in. So
okay.
So if any suggestions are there,
I guess the first choice, I guess I mean, so again, I'm just thinking off the top of my head. I don't know, so I don't know if this is of any use whatsoever. But in general, you with Nevanlinna theory, of course, one theme is you have some object, which is in the classical theory a disk, and also in the standard disk, it's also a disk. So you take a disk. The disk is determined by one number, which is the radius, and you consider what happens as that radius goes to infinity. Right? So you write down Jensen's formula in the disk. So I guess the first thing you have to decide in the half disk is what is the analog? What are the little balloon things that you're slowly inflating, and in the end they're going to approach the whole disk, or half disk rather, right? Because I don't see a particularly privileged answer to that question, right? So obviously if it's a disk, you just take a small disk and you just blow it up and you get the whole thing. Even in the half plane, it's a bit complicated, right? But often there they also take a disk, you chop out a little bit at the origin because it might be a problem. and you let the disk get bigger and bigger and the center get higher and higher, and eventually that would cover the whole half plane. And Nevanlinna also considering a kind of a disk with some, you know, chunks out the side. But the point is that there are different ways of doing it, and even in the half plane, some work better than others, in the sense that some give you a useful lemma on the logarithmic derivative, and others don't. And so that would be, so I don't know the answer to your question, but that would be the next question that I would ask. What is the natural blob? You know, what's the one parameter family of regions, right? What's the one parameter family blobs that you're going to deal with that fill up this region? And is there anything special about them? Because if they don't have certain nice properties, excuse me, then the equations work out in a nasty way. Sorry. So for example, in the disk, you know, when you're integrating around the circle, you only end up seeing the modulus of f if you choose everything right. And that's why we have the log of the modulus of f turning up, because the angular part kind of just drops out of everything. But when you're integrating along different regions, then that's not necessarily the case. And if you're not careful, you can see the argument of the function as well. And we have less control over the argument. I think your video has frozen.
Thank you, sir.
Or I've bored you so much that you've become catatonic, one or the other.
Thank you, sir. Thank you. Internet ಹೋದ್ರಿ?
Sorry, Subhash, you have your hand raised.
ಅವ್ರು ಮ್ಯೂಟ್ ಆಗಿತ್ತು ಸರ್, ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ರಲ್ಲ ಅವ್ರನ್ನ.
ಸರ್ ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ರಿ ಅವರಿಗೆ.
Go ahead, Subhash.
Hello, sir.
Hello.
Hello.
हाँ, Mr. Subhash, you can ask your question.
Please.
Yes, sir. For the matters of real analysis, that is what we are treating there.
I'm sorry, I think I've lost your audio. I can't hear you.
Subhash sir, you can ask your question once again, or you can type it in the chat box.
Okay, sir. Okay.
Yes, sorry, I heard you introduce yourself, but I couldn't hear anything after that.
Sir, I have asked him to ask a question in chat box. As soon as he types in, I'll just let you know.
Okay.
Okay, sir.
Well, I just, while I'm waiting, I just realized, I don't know if they're still here, 15 minutes ago, somebody asked, does complex analysis help to solve real life problems? If so, please explain. Well, perhaps it depends what you mean by a real life problem, I guess. But as I said, I've often had to teach engineers, and it's a service course. So, we don't, to some extent, we just want to keep the engineering department happy, because then we get some money from the engineering department. but the engineers demand that we teach complex analysis. So it's not a case of us saying, oh, well, this is a really boring course, so I'll throw in some complex analysis so that I don't get bored. It's the engineers really wanting complex analysis. And this work that I talked about for these partial differential equations in fluids and so on, that's often cited as the biggest advance in applied mathematics in the second half of the 20th century. And that is totally reliant on complex analysis, this scattering data that I referred to. So you're trying to solve a water wave problem, which comes down to solving a problem in quantum mechanics. So you can just take the problem in quantum mechanics if you like. You have a beam of particles that come in, and then a beam of particles go out because there was something happening on the inside, and that's governed by the potential. The gradient of the potential is the force. So that might be your atom or whatever. So at one level, you want to say, okay, if I know what's happening inside, I've got a helium atom and I throw in some waves of certain frequency, what stuff comes out? Some gets reflected, some goes through. That's a direct scattering problem. And the harder problem is, suppose that I know what happens if I do that experiment, right? I beam some stuff in, some stuff comes out. I want to know what was in there. Again, that's the classic kind of inverse problem for doing X-rays and so on. That process is all complex analysis. It reduces to this Riemann-Hilbert problem that I mentioned. The scattering data that I described is given by the poles of certain functions. So the function that gives you, there's a reflection coefficient, so that's how much of your beam of waves gets bounced back, and there's a transmission coefficient, that's how much stuff goes through. You have to consider these things in the complex plane, and all you care about are basically the location of some poles and some residues and how those things evolve. And yeah, the method, all I can say is, you know, the methods really are complex analytic, and many much simpler problems are just much easier to rephrase in the complex representations of objects that are hard to see where they come from otherwise. Sorry, I'm just quickly reading the chat here.
Sir.
Yes.
Usma want to know means books on Penlew differential equations, sir.
Yes. So there aren't very many. It also depends on which aspects you're looking at. So because again, one of these things with integrable systems, there's a more complex analytic approach. There's a more algebro-geometric, which is still complex analytic, but you know, it's much more algebraic geometry and symmetries kind of approach. So the approach that's more complex analytic, that's, you know, solving these things which basically means getting some nice representation of the solution. In terms of Riemann-Hilbert problems, there is a book by Focus and Itz. Okay. I've got, that's embarrassing, I've got one of the authors wrong. Well, anyway, it's so Focus and co-authors. There's also some work that looks a bit more of the symmetries of these equations. So there's a book by Noumi, N-O-U-M-I, and that looks at the Pain-Levé equation. It's called Pain-Levé equations through symmetries. And there are some long papers. So I just sent some to some students. So there is a paper that looks again at this algebro-geometric approach. The idea there is that you're trying to find the natural space on which these functions want to live, the equations want to live, and you have to do what are called blow-ups. You get certain indeterminacies where the equation is not defined, and you add points to the natural space by a process called blow-ups. and there's a very good review article. If you just drop me, if you want to drop, I can send you some references.
Okay, sir. Thank you.
You're welcome.
Sir, I have another one question, sir.
Please.
Sir, we have heard about the real integrals. Sir. So that is for area function. There is a area function, sir, that we know. But what about the complex integrations, sir?
Well, complex integration is usually because you're in a two-dimensional space. So usually you're integrating along a curve. So you're adding up contributions of a function along the curve. And the nice thing about the analytic functions, the functions that are differentiable on an open set, is that the answer that you get is independent of the particular curve that you take. So complex integration ultimately is the thing that makes complex analysis the most useful in other areas, especially in engineering, because you can take an integral that you're trying to do on the real numbers, often from -infinity to infinity or something like that, and you can relate that integral to an integral in the complex plane, where we have a lot more control over things. We have a lot more theorems and tricks that we can apply, and in the end, we can use those tricks to evaluate the real integral. And this is the kind of thing I think that Panleve had in mind when he said that the shortest path between two real truths lies in the complex domain. So often you start with a real problem, it's going to have a real answer, but to get there quicker, you want to think of it in the complex plane. And complex integration is one of the biggest tools that you have. Because often doing an integral along a closed contour in the complex plane is often something that can be evaluated without doing any integrals at all. In the sense that if the function is analytic on the inside, you know the answer is 0. And if it's not analytic, but you've got some information about the singularities, then that's enough to evaluate the integral without actually doing any calculus effectively.
Thank you, sir.
You're welcome.
Professor, I have a question.
Please.
Well, one professor, Keith Carney from Cambridge University, I heard that he was working on Nevanlinna theory by introducing the hyperbolic metric. Is there any progress in that direction?
I don't know. I haven't seen Keith Carney for quite some time. But certainly, hyperbolic metrics are used in Nevanlinna theory in different places, particularly when you go to higher dimensional Nevanlinna theory. Yeah, I certainly don't know anything in particular about what Keith Kahn is doing. And yeah, in general, I don't know anything particularly precise. I guess you have the same issue, when you're looking at that disk type results.
Thank you.
Sir, questions idre ಕೇಳ್ರಿ ಸರ್.
ಇಲ್ಲ ಕೇಳಿದ್ನಲ್ಲ.
ಹಾ ಸರ್. Thank you, sir. Thank you, sir.
You're welcome. Thank you.
Thank you.
Okay, so I hope to see you tomorrow.
Thank you.
Unless anybody else has anything they want to say.
Thank you.
Sure, sir.
Okay, thanks again.
Okay, so we conclude today's session, and again we'll be meeting tomorrow. Thank you, one and all.